Okay, let's start. Okay, welcome everyone. This is a course in Neural Network 1. The course is going to be taught in English, as you can see. Jonathan is giving the course. He's now on the way here from the airport, so he's supposed to come, I think, in the next 2 hours. So we really have 2 hours today. My name is Ron. I'm the TA of the course. This is my email. It's Darshan Ran. So as I said, Jonathan is teaching the course. It's 3 hours course and then another hour of TA, Gilgul. So it will be, usually Jonathan will teach the first 3 hours and I will give the hour afterwards. And there will be another extra hour. So this is not mandatory, of course. This hour will be, so we need to decide together when it will be. For now, it will be, today we are not going to have it, but it will be here from 2 to 3 every week. Besides today, in this extra hour, what we are going to teach, either is going to be an exercise that's going to help you with something that you missed something from Jonathan class or something like this, or some analytical derivation that you didn't understand, or stuff that I think that can help you in understand better the course. This is usually for people that have that their background in math is not that good, maybe, but it's open for everyone, of course, and you are more than welcome to come. For example, I think next week what I'm going to do, I'm going to talk about left and right Ewing vectors. So this is something that Jonathan is going to use maybe next week or 2 weeks ago, 2 weeks from now. So if you are not sure what is left and right Ewing vectors, you feel uncomfortable with what Jonathan did in class, then you are welcome to come. Another example, I will talk about the central limit theorem. I'll talk about Fourier. So all kinds of stuff that you should know. Most of you, if not all of you, but still, if you feel that you need some help in this, that you're welcome to come. And also, we'll see how it goes during the year. Maybe you will have questions, and then we just maybe like open question hours. So this is an hour for you. I know that 4 hours it's a lot, so we take a 1 hour break, and then we can eat something. What? Students have a class at that hour. Okay, so so today we don't have, so it doesn't matter, but we'll choose one of the students, and you can arrange the hour. We'll see, usually it's like 5 to 10 students are taking this hour, so these 10 students should choose the hour that is best for them. It's not an hour in the system. Exercises. So it's not every week, but we will have something like 7 to 8 exercises. This depends on how many lessons we are going to have. You need to submit, you should ask Jonathan again, but usually you need to submit n-1. And it's mandatory, and I think it's 30%, maybe it's 20, but you should ask Jonathan. So it's 30% of the grade. Okay? Usually you should submit it in 1 week or 2 weeks, depends on what's written on the exercise. And we are going to be strict with this dates, and the reason is that there is a guy, Matan. He is checking the exercises, and Matan is very strict as well. He wants to give you the exercise back after a So we don't want that someone will submit the exercise, I don't know, 3 or 4 weeks after we gave it, because we want you to learn from the solution. Matan is going to actually check all the exercises and give you a full solution. So please submit the exercise on time. We have a Moodle. Okay, so this is the website. We have a Moodle. If you have any questions about the exercises, of course you are welcome to come and you are welcome to send me an email or to ask me in class. But if you have something that you think is more general, for all the class, you should ask it in the forum. And the reason is that usually people ask the same questions, and then in the forum I can answer to all of you, and everyone can see it. So I will open a forum in the Moodle for the students, and then you can ask whatever you want, and especially ask stuff about the exercises.
Yes. I think we need an enrollment key to enter Moodle.
Yeah, of course. Wait, I'll get to it. So now there is nothing on the Moodle. After the class, I'm going to put there the first exercise. I'm going to put there lecture notes from last year of a student named Yafin Gulam. And the course is going to be similar to last year, so I think it's going to really help you. But if there is someone that is taking notes, especially in LaTeX or Lich, so you can bring me the notes. I will put it on the website every week. This is what I did last year. And this student, of course, will get some bonus. The last thing is that the course is recorded, as you can see. And I'll put a link for the website. You need to see that I and Jonathan are wearing this, and that it works. Okay. Otherwise, you won't hear anything. So pay attention. Okay. And if there is a problem with the battery, so you can go to the secretary and ask for a battery. So I'll try to put it, see that Jonathan is doing it as well. And there is an enrollment key, which is LSEC. All right. So everyone can enter, even if you are not enrolled to the course. Any other questions before we start? No, I answered everything. Okay. Okay. So what we are going to start. Yeah.
Are all the exercises going to be theoretical, or is...
So the exercises are part of it is stuff that you need to do, like analytical solutions, and stuff that are going to be simulations. So I'm going to explain how to do the simulations, and the reason is that usually we can solve a lot of things in theoretical neuroscience, but there are a lot of things that we cannot solve and we can simulate. And this is one of the most important methods that you are going to learn in this course, how to simulate spiking neurons, how to simulate a network of neurons. So these are, every exercise is going to be a theoretical one and a simulation. Yes?
Will the subjects of the extra hour be published in Advances Neuroscience?
I will try to say it, so usually it depends on what you want me to teach, but I will try to say, I'm not sure I will have time to publish it, but either I tell it during the hour that I'm teaching, or I'll put it in the Moodle before. Okay. So today we are going to talk about the passive membrane. So a cell in our brain is called a neuron. This neuron has a membrane. This membrane, they separate the outside, the environment, from the inside of the cell. Okay. And ions cannot go from the outside to the inside of the cell and vice versa because of this membrane. So this membrane acts as a capacitor with letter C, and there is on this membrane there is also channels, ion channels, that ions can go from inside to the outside and vice versa. And these ion channels, they have resistance that we call R. And this passive membrane is actually an RC circuit, and there is an equation that explains how the voltage on this membrane evolves during time. So this voltage depends on time. So we describe it in the differential equation of the voltage. And I'm going to write the equation, and all the stuff that I say now in the last minute, Jonathan is going to explain in 2 hours how to derive it, and what does it mean, what does it mean capacitance of the cell, what do I mean by resistance of the cell, what are the ion channels, what are ions, okay? So for us, it's an exercise. Jonathan is going to derive this equation, and now we're going to see and to solve this equation for different inputs to the cell. So the equation is dV dt. This is the equation of an RC circuit. Again, Jonathan is going to elaborate about it. It has a time constant tau, and is equal to minus V of t plus R is the resistance of the ion channels times the external inputs that we give to the cell. So again, Jonathan is going to talk about it in more details, but a cell, a neuron, a cell in the brain, is going to be something that looks like this. It has inputs that are called dendrites, and it has an output that is called axon, and Jonathan is going to talk about it. And we can put an electrode and inject a current to the cell, and this current is going to change. So this current is this current over here, and according to this current, the voltage of the membrane is going to evolve in time, according to this equation. So this is the differential equation that we are going to solve. I need to give you what is I of t, of course, and I need to give you another thing. What do I need to give you? So I need to give you also initial condition, right? If I give you initial condition, it's a first order differential equation. There is only one unique solution for this equation. So we will say that V at time t0 is equal to some V0. Okay, let's solve this equation. Most of you know how to solve it, I'm sure. How do we solve this type of first order differential equation?
We get a solution.
We can get a solution, but that's not a pedagogic way to do it. So what we can do? So we solve it using integrating method. So I'll give you later the general solution. Let's see what the solution in this case. So I'm moving V of t to the other side. I'm dividing by tau. I'm getting dV dt plus 1 over tau V of t, which is equal to 1 over tau I R times I of t. And now I'm going to multiply by integrating factor. The integrating factor in this case, and I'll give you the general solution later, is e to the t divided by tau. So what we get is dV dt times e to the t divided by tau plus v of t multiplied by 1 over tau e to the t divided by tau, and this is equal to 1 over tau r I of t times e to the t divided by tau. And why did we do this trick? So the essence is over here, right? What we see is that, in fact, this is a product of this is the derivative of product of two functions, v of t and e of t divided by tau. Right? The derivative of the product of two functions is the derivative of the first function times the second one plus the second one divided by the derivative of the first one. And what we can do now is we can integrate both sides, and we will integrate it from t0 until t. t0 is the initial condition. So we get that the derivative of v of t e to t prime dt from t0 to t is equal to 1 over tau, the integral of Ri t prime e of t prime divided by tau dt prime from t0 to t. And now the integral of the derivative is just the function inside, so it's v of t e of t divided by tau when I'm putting t minus v of t0 e to the t0 divided by tau, and this is equal to 1 over tau, the integral from t0 to t I of t prime e to the t prime divided by tau dt prime. Now I want to isolate v of t, right? What is the... I remind you, the solution for an ordinary differential equation is a function, is v of t, right? This is what we want to get. So we want to get v of t. Therefore, v of t is equal, so I'm taking v of t0 to the other side, and I'm dividing by t, by e to the t divided by tau. So I'm getting, this is from the first term, and from the second term, we get 1 over tau, the integral from t0 to t, I of t prime e to the t prime e to the minus t prime divided by tau dt prime. So this was very, very fast, but you should all, I think all of you saw how to solve the ordinary differential equation, and if not, then you can do it in the extra hour if you have some question. I can just write again here the general solution that we just got, because we are going to use it. So v of t is equal to v of t0 times e to the minus t minus t0 divided by tau, plus the integral from t0 to t, r I can take outside, I of t prime e to the minus t prime divided by tau dt prime. So I'll try to go slowly on stuff which are, I think, you know, less, but is there any questions about how we derive this equation?
How did you derive the 1 over tau?
What?
How did you, is it just missing? The 1 over tau?
Thanks. And if there is something that you don't understand in my writing, please stop me, okay? Any questions? Okay, so the general way to solve first order differential equation using an integrating factor so it's very easy to prove it. You can see it on Wikipedia if you want. So if we have differential equation that looks like this, what is g of t in our case? 1 over tau, right? What is f of t in our case? Right? G of t is 1 over tau, and f of t is also this term over here. So if we have differential equation that looks like this, then the solution is going to be, so the integrating factor is the integral of e to the, is the exponent of the integral of g of t prime dt prime, and x of t is equal to the integral from t0 to t of I of t prime, f of t prime, dt prime, plus a constant that we need to get from the initial conditions divided by I of t. So you can go and see that this is how we get it. And the idea of how to prove this this solution is just similar to what we did here, but just take the integrate factor to be this. Okay.
How do you know to choose the integral and factor?
What?
How do you know to choose the factor?
So the prefactor, so see? How do I choose to choose this one? Right, so I know already how to solve it, right? So I know that this is what I have to do. But for us, g of t prime is 1 over tau, right? So I'm just taking e to the 1 over tau, right? The integral of t divided by tau, right? So I just put it over here. But the way to do it is just to multiply it by some integrating factor I, and to continue and see what is I at the end. Just this is very in several lines to prove it. You can see it in Wikipedia. Okay.
And what is T prime?
So t prime is an integrating variable. Okay.
It's not the same variable.
As t. No. Right. So it's an integral. This is a function of t.
Okay, because you're infinity.
I can write it as f, for example, right? This is the integrating variable. It's not t. Okay. So now let's start to see, so we're going to give the cell different inputs, and let's see how the cell is going to react. This is a typical RHC circuit, so if you already learned something like this, you know the solutions, but let's do several examples. So the first example is we give a constant input, which is 0. Right? I of t is going to be 0. So this is t, this is I of t, and we just put I of t to be 0 all the time. Let's solve and see what we get. So I will remind you we are looking for what is v of t. So in case of I of t is 0, all of this term is 0, right? And the only thing that we get is that v of t is equal to e to the minus t t0 divided by tau multiplied by v0, which is the initial condition, right? v of t0 is just v0. And this equation is true for all t which is bigger than t0. Okay? Everything that we write here is for t which is bigger than t0. So somewhere there is the initial condition t0. In this initial condition, where I is still 0, but in this initial condition we start the system in a way that v at t0 is v0. So we are starting here, and then we have a decaying exponent with the time scale tau, and we go to 0. Okay, this is clear? Good. Let's take now okay, so before continuing, what you see is even if we don't insert anything to the cell, we have a decaying term at the beginning that comes from this initial condition. So if you don't care about this initial condition, we can say that we waited enough time, and only after a long time we did something to the cell. So this decaying exponent already decayed. Another way to say it is to say that the initial condition is not a t0, but which is equal to minus infinity. Okay, in this case, case, if t0 is minus infinity, so this term goes to 0, right? So this is a different way to say, I don't care about the initial conditions because they're already decayed, and then I need to write v of t as r divided by tau, and the integral is from minus infinity to t of I of t prime e to the minus t prime divided by tau dt prime.
Why? In minus infinity it's going to 0?
So I'm putting so I don't.
In infinity, no?
So I'm putting minus infinity instead of t0. So this term is infinity times minus. So I have e to the minus infinity,
You need parentheses?
and this is outside,
What
right?
does it mean to plug in minus infinity t0?
So just let's think about the t0 is very large, right? T0 is something like that happened 2 years ago, right? So this number is very large. It's large with respect to this tau over here. So all of this number is very large. E to the minus something which is large is something which is very close to 0. So it means that this term is close to 0. In other words, I don't care what was t0 2 years ago because it's already decayed, and I care only what happens now when I'm inserting some input from outside, right? So this is how, in other words, every time me or Yonatan will tell you that the initial condition decays, it means that we think that it happened a long time ago and we did something, we are doing now to the circuit something which is this current step, which is where the initial condition already decayed. Okay, so we are going to continue with this equation, all right? But remember that every time that there is an initial condition in the beginning, it is decaying. Okay. So let's look at another input, which is a constant input. So again, this is I of t. This is t. And somewhere at capital T, we insert an input which is constant with amplitude I0. And we want to see how the voltage is going, how the cell is going to react to this input. So of course, before inserting the input, it's like the solution before, it's 0, and we want to see what happens here. So let's insert it to the equation. So we are looking at I of t, which is either I0 for t bigger than capital T, and it's 0 otherwise. And another way to write it, and this is one of the goals of this course is to make you better in simple methods in math. So let's write it in another form with the theta function, theta of t minus capital T. And let me remind you what is the theta function. So every time I write a reminder, it's either you saw it last week or in Yonatan class, or it's something that I think most of you should know. So the theta function, theta of x, is equal to 1 if x is bigger than 1 and is equal to 0 otherwise.
I thought it changed to 0.
What?
The theta function.
0.
0 when x is negative and 1 when x is positive.
0. Okay. So this function is actually what is written here. And let's plug it inside this equation. So v of t is equal to r I0 divided by tau, the integral from minus infinity to t of theta of t minus capital T, e to the minus t minus tau, the t minus t prime divided by tau dt prime. There's nothing I didn't say. I told you, I know that it's very easy if I'm giving you my lecture notes, so I'll put it online on the Moodle after class. Okay? If you don't want to write, you're welcome. But if you do write and you write it in LaTeX form, you get a bonus. So do it. Okay. So this is the equation. Let's solve it. So this theta function, the only thing that it tells us, And this is, of course, for t bigger than capital T. And the only thing that it tells us is that this function over here is 0 unless t is bigger than capital T.
We still in where the initial condition is this case?
Yes, this is why I didn't write this first term, right? I'm lazy, I don't like to write it all the time. I just can say that it's 0 or that it already exists. Okay, so let's write the solution. It's from t to capital T of e to the minus t minus t prime divided by tau dt prime. And we just need to do the integral. So the integral of this exponent is just this exponent, and we have this tau over here. So it's e to the minus t minus t prime divided by tau. But we need to put it in the limits t to t prime. And this is equal to Ri0 1 minus e to the t minus capital T divided by tau. And this is, of course, if t is bigger than 0, than capital T, and 0 otherwise. So until capital T is 0, and then here it's going up with this decaying exponent, but it goes up because the 1 minus. So we go up until where? What is this number? Right, it's Ri0. Okay. So this is how a constant input at time t looks like. Any questions about this voltage 100% in time, why it looks like this? So you see here that we are assuming that you know several stuff. We don't assume that you know other stuff. Jonathan will probably assume that you know more stuff. But if you have anything that you don't understand, please ask me. If you feel that we are going too slowly, then we will speed up during this upcoming weeks. But again, if you think that we are going too fast, please tell me. And anyway, we have the extra hours to help. Yes.
How did you do the step before last?
This one? I just did the integration of this term, right? It gives me this term over here, and I need to put the limit t in capital T. So I just put the limit, right? So t, this is e to the 0, this is 1, and this is the other one. Okay. 3. So we are looking now at the other situation where we have a constant input that stops at t. And we want to see how v of t looks like. So how do you write I of t in this case? Right, it's equal to I0, so we have the I0 until t. Right, so it's exactly like before, but the difference is that now it's capital T minus t. Right, it's just the reflection of this function. And this gives us, again, 1 until t, which is 0. So this is how we write it. And again, we can plug it into the equation. Let me just, this is something which is very similar to what we did, so let me skip this step. What we get is Ri0 times e to the minus t divided capital T divided by tau if t is bigger than capital T, it's 0 otherwise. Okay, this is straightforward. It's exactly what I did over there. So how does it look like? Sorry, it's not 0, it's I0. Okay, so somewhere back in minus infinity, we insert a pulse which is positive. We got to Ri0 as before. And then at t, we stop the input. Then we're going down how do we go down? Exponential, if this is e to the minus t, t prime divided by some. Okay?
Isn't there a stage that should go up in the beginning?
What?
Isn't there a stage, I mean, it starts from 0, right? So shouldn't it go up?
No, it starts from I0. Right? This is why I'm saying we forgot the initial condition. I started somewhere back then, like this, right?
So here you start from 0.
So I started somewhere back there in 0, but I forgot this initial condition, and then I went up to I0. So this is why you see here there are 3 points, right? Because I started back there in infinity, and then I'm looking what happened now. Okay. Let's take something which is a little bit more interesting. It will be a combination of 2 and 3. So now what I'm taking, let's do it here. This is 4. And now I'm taking a pulse. So there is this t that we have, capital T that we had before. And now I'm taking a pulse, from t minus delta divided by 2 up to t plus delta divided by 2. Right? In a way, it's a combination of the what we had before. This theta function, which is this one, and this theta function multiplied the theta function, which is this one. So how do we write this? How do you write this term I of t? So it's going to be a product of these two theta function, right? The first one that starts over here. So this is, okay, so first we have I0, and then we have the first theta function that starts at t minus delta divided by 2. So this is theta of t minus capital T minus delta divided by 2. And I need now to multiply it by the other theta function, which is this one, right? Which is what?
The delta divided by 2.
Which is the other way around, right? T plus delta divided by 2 minus t. Okay, so this is I of t. This pulse for duration of delta around capital T. Let's solve this equation. So V of t is equal to I0R divided by 2, the integral from minus infinity and, okay, so the integral is from minus infinity to capital T, and we would like to know what happens if we are inside this pulse. So the integral is going to be from t minus delta divided by 2, right, because it's 0 before, up to some capital T. Alright, so let's make it even more easier. Let's look at what would be up to capital T. Okay. Okay, let's go back to it later. Okay, so to put a place, we'll go back to it after I see that I have some small correction here. So let's go back, let's go to 5 and we'll go back to this one. So 5, we didn't see the solution now for I of t, so this is what we had before. We didn't see the solution. I'm going to go back to it in the later, but what we are going to do now is what, okay, this is delta. what we are going to assume now that this input, what we are going to assume now that this input is coming from delta, which is infinitesimal small. So this delta is going to be very, very small. And this I0 is equal to some Q divided by delta. So this input is going to be very large because delta is very small. Okay? In other words, let's write it as before. I of t is equal to I0 theta of theta of t minus minus delta divided by 2 times theta t plus delta divided by 2 minus t. And now we are going to take the limit of I of t when delta goes to 0, when I of 0 is equal to q divided by delta t. By delta, sorry. What does it mean? It means that we take delta smaller and smaller and smaller, and then this height over here is going to be bigger and bigger and bigger, right? So in this limit, what happens is that delta, where delta is getting smaller and smaller, the input is getting bigger and bigger, but for a very short duration.
What is Q?
Q is a parameter that I'm taking for now, and I'll say what it is. But Q is just something that does not change with this delta, and when I'm taking delta to 0, I'm actually taking an input which is very, very narrow and very, very strong. So in this limit, what we get is that I of t is just q times delta of t minus t, the capital T. And again, let me do a reminder here of what is delta. So this is the Dirac delta function. Dirac delta function, delta of x minus x0. The integral from minus infinity to infinity is what? Is 1, right? So this delta means that I have some measure that is concentrated around x0, and around this x0 I have something that goes to infinity. So it's everywhere it's 0, and when I cross it, then it's 1. Right? This is what this integral says. And another thing is, what is the integral from minus infinity to infinity of f of x, delta of x minus x0? This is just f of x0. And other stuff about the delta function, if you don't know Dirac delta function, go to Wikipedia, it's right over there. Okay? So let's solve this part over here. What is v of t? V of t in this case, and before this. Okay, so now if you do the integral from minus infinity to infinity of I of t, of course in the limit of delta goes to 0, then we get the integral from minus infinity to infinity of delta of t minus capital T dt, and q goes outside, and this is equal to what? This is equal to q, which is the total charge that was injected to the cell, right? We are looking at the entire input that came to the cell. This is, in fact, the integral over here. This integral is called the total charge, q. This is why the sign is q. Q is the sign for charge. Okay, let's finish by writing the solution for this integral, and then we'll take a break. So v of t is equal to the integral of from minus infinity till t of qr divided by tau, delta of t minus capital T e to the minus t prime divided by tau dt prime, and this is equal to what? So again, we are in t bigger than capital T. So it's written over here, right? If you have a delta function and some f of x, then the solution is just to put x at 0 inside the function. The solution is just qr divided by tau times e, where I put, instead of t prime, I put capital T, so it's minus t minus capital T divided by tau. And how does it look like? So if this was I of t, the function of t, which is a delta function around t, then v of t, this function of t, is 0 until capital T, and then it decays. And it decays from something that starts at qr divided by tau times 0, right? Times 1. And then it decays. Such that the integral over here is what? Okay, let's leave it open and go to the right. Yeah. Let's start the. Let's go to break and come back in. Okay. לא, זה לא מינוס, זה המינוס כאן.
לא, מינוס בין שני סטייטמנטים.
אם יש... זה כאן. אבל איך זה, כאילו, את הכפול לא הבנתי.
לא, כי רק אחד הם רק שווים ופה, אז זה
כפול בזה. כאן, כאן זה 0 וכאן זה 1. וכאן אני הפכתי את ה...
אני לא חושבת שזה ממש נורא מסוכר. יש לי את הקפה הטעים, כאן?
הכפל שלנו. נתנו את הנפש, נתנו את הנפש.
אבל זה גם כאילו, זה חמיד.
כן, זה אמין באמת.
אנחנו דנה דיברת לנו.
גם זה איתי. כאילו אני רוצה את
העניין הוא כמו שראית מהמעבדות האלה,
זה עד 6
זה גם ארוך וזה גם בסדרה ואת צריכה להכין דברים, את לא יכולה לבוא פלולס כאילו מהטיסה, כאילו בדיוק, כאילו ואם את טסה לארצות הברית ואת צריכה לעבוד כל הזמן על כאילו לימודים פה לכל דבר,
לא, שמה אם את עושה את זה שם בבית, שם בבית, אז שום טעם. אם את עובדת בטיסה, זה עדיין שווה, לדעתי. אבל אם זה מטריד אותך שמה ואת אומרת, רגע, בסוף לפני, אולי נשב פה, רגע, בגלל בסוף אני אצא מהסטופה כדי שיהיה לי זמן לשבת שם ולעבוד.
כן,
כן, אז למדנו את הפונקציות והבחירה בדרך כלל, אבל זה לא אינטואיטיבי, ואז מה שקורה שיושב בכיתה, אתה רק רואה את זה, ולראות את זה במקום המנות, ואתה לא מספיק את שלוש את זה, זה המון, אני לא יודע מה אפשר לעשות, אפשר להתאים את הזה למיטה הקטנה שלנו, שלא עד כמה שמורים על זה.
זה בסדר, כמו שאמרנו, שזה יש את השעה שהמטרה שלה שכמובן את הדברים האלה יש להם מטרות, או שעוד דברים שיעזרו להבין על דברים או שאני אעשה דברים שעשיתי רק יותר לאט בסופו של דבר יש לי פה בכוונה שתי סיבות לזה שאני רץ, אחד או שיונתן לוקח לי קצת מהשיעור ואז אני לא מספיק, אין לי ברירה, אני פתח עד לרוץ, או שאני טיפה רץ או שאני לא עושה את כל החומר, או שאני לא שם לב, או שזה דברים שהם אמורים להיות עם תשארת קצת בבית, זה סבבה. זה דברים שעשיתי פה, וזה רק תראה את זה כל הכול, אתה צריך להיות על הדברים שאף אחד לא יישאר מאחור, וגם שזה לא יהיה too much. דברים כאן, דברים שהם לא, אתה רואה את הפעם שם, גם אם עשית, כל הדברים האלה עשיתי. עשיתי אינטגרציה דלטה, ופעם שאלתי אותה בפעם I've been told that those of you who are not aware of what I'm of this notation, so if you are aware of it but you didn't do it by yourself, so I've been told that it's a little bit too fast. As I said, these are stuff that you can practice at home. All right. So usually I'll go slower, but I'll go slower. If not, please tell me. And let me try. So I'll skip one of the stuff that I want to do, and let me try to go slower in the next hour. Okay. And maybe we'll go back to it later if we have time, or if Jonathan won't come from the airport. Let me go back now. Any other questions? No. Let me go back to 4. This is what we had before. And just we're looking now at what is v of t, as function of time, what is v of t. And we want to see how it looks like inside this part that we have over here. So let's do this integral. This integral is just Ri0. The integral of the exponent with the tau is just the exponent. And we need to put the limit from t minus delta divided by 2 up to t. Okay?
Minus is on the entire
Yes.
thing, right?
The minus is here all the time. Okay? This is just Ri0. And I need to put the limits. So first I'm putting t. So I'm getting t minus t is just 0. So e to the 0 is 1. Minus, I'm putting this limit. So it's e to the minus t minus delta divided by 2. Capital T minus delta divided by 2 divided by tau. Okay, so this is what happens if we are inside this pulse. Now, what happens? Okay, so first of all, how does it look like? It's 0 until t minus delta divided by 2, and then it goes up, right, because this 1 minus this exponent. It goes up, and it goes up until it gets to t plus delta divided by 2. What is the number over here? So let's just write it. I want to know what is v at t plus delta divided by 2. So I'm just putting t plus delta divided by 2. Right? So I'm just putting t plus delta divided by 2. So it's Ri0 multiplied by 1 minus e to the t plus delta divided by 2 minus t plus delta divided by 2. So this is delta divided by tau. So this is what happens here. Okay? Now, if we say that delta is small, we can get an estimate, a better estimate, not a better estimate, but some estimate of this function using Taylor expansion. So it's doing Taylor expansion of e to the x. So it gives us, here we have 1 minus the Taylor expansion of the exponent is just 1 minus, wait, sorry, plus delta divided by tau plus all the other terms, right? Taylor expansion of the exponent, I can cut it in the linear term. And this gives Ri0 divided by times, right, so 1 and 1 is have minus sign somewhere? Where? Here? Yeah. this minus here, right? So here I have minus, so here it's a minus sign, right? So it's delta divided by tau. Okay. So this gives us this peak over here. And then from here we go back, we start from this initial condition like before, and we go back to 0 with exponential decay. Okay. You had a question? What about the minus? Okay. Okay. Let's do now something.
According to the, like what we did with the constant.
Yeah, so the decay is like the constant, but now, okay, so let's write it. So V of t is equal to Ri0 times 1 minus e to the minus t minus t plus tau divided by 2 divided by tau if t is inside t minus delta divided by 2 t plus delta divided by 2, right? And if t is bigger than t plus delta divided by 2, then it's exactly like before. We have this decay of 1 minus e to the minus t minus t plus delta divided by 2. Right? This is the decaying exponent that we have, and this we need to multiply it by this peak over here, which is just v of t at t plus tau divided by 2. Okay? Okay. Let's now see what happens if we have an oscillatory input. So I of t is equal to sum I0 times cosine omega t. Let's see how it looks like. So this is I of t, this is t. At t equals 0, we have I0. Let's say that we measure our time in seconds. So let's say that this is 1 second, this is 2 seconds, etc. And I remind you that omega is equal to 2 pi f, where f is the frequency. So if I want to plot this function with frequency which is equal to 1 hertz, 1 hertz, it means that it comes every 1 second, we go back to the peak. So I'm starting, cosine at 0 is just is just 1, so I'm starting at I0. I'm going down and I'm going back after 1 second, again to I0. Right? The minimum is minus I0. And again, I have another cycle until I go back to 2 seconds in the second cycle. So this is equal to f, which is 1 hertz, meaning that the peak is coming back after 1 second. And if I want to look how the input look for 2 hertz, so in 2 hertz it means that the peak here, we will return to the peak after 2 seconds, after 2 cycles. So we have another cycle here, it will look like this. Right? This is, and we'll continue, of course. This is frequency of 2 hertz. Okay. Now, let me give you another reminder about complex numbers. So I can do it without complex numbers. The reason that I'm doing it with complex numbers is that it's another method that you should encounter and you should know in general and when doing this course. So this is again a reminder. Z is a complex number. I can write it in 2 forms. The first is a plus ib. This is the real part of the number. This is the imaginary part of the number. And I can also write it as some amplitude times e to the I theta, where this function e to the I theta is just cosine theta plus I sine theta. Okay? Well, again, this is the imaginary part and this is the real part. This was just a reminder. Okay, and so this was just a reminder. And now if I want to write this function in a different way, I can write it just as I0 times e to the I, theta here is omega t, but I need to take the real part of this function. If you go back here, you see that I just wrote exactly the same stuff. A here is 0, is 1 in this case, if I'm looking at cosine omega t, and theta is just omega t. Okay, so I just wrote the same function in a different way. And now let's try to solve the equation for v of t. So what is v of t? V of t, I'm just putting it again in the equation, is IR divided by tau, the integral from minus infinity to t of the real part of e I omega t times e to the minus t prime divided by tau dt prime. Now, the real part, because this is real and everything is real inside in this function, I can just take the real part outside. You can convince yourself that. So what is the integral? Integral is kind of sum, right? It's sum of many numbers. So of course the real of the sum of many numbers is just the sum of the real numbers, right? So I can take the real outside. So this is what I'm doing. And e to the I omega t times e to the minus t prime divided by tau is just the summation of the two, right? And this is why I did it, because it's easy to solve this kind of equation, right? To know how to do the integral of exponent. So this is why.
T prime, no?
What? T prime, right? This is T prime. This is T prime. Why it is T prime? Because it was I of T prime, right? And I put cosine of omega T prime. Okay, so this is equal to I0R divided by tau, the real part of the integral. Let's combine the two terms in the exponent together. We will get e to the 1 plus I omega tau multiplied by t minus t divided by tau dt prime, right?
Why is there
I just do the just
Ah,
okay. Next, what we're going to do. Let's leave this over here. Okay. Now we know how to solve this equation, right? This is just the integration of exponent, so it's equal to I0R times the real part of 1 divided by 1 minus plus I omega e to the I omega tau plus 1 t prime minus t divided by tau from minus infinity to t. Right, I just did the integration. Tau went because of this tau, and this came because of this term over here. Okay, let's put the limits. We get I0R. You have a question? Okay, we have I0 times R times the real part. So again, I said this tau over here, you went with this tau that came from the integration. Right, the derivative of this guy over here gives me I omega t plus 1 divided by tau. Here I compensated for this, and this is the tau. Okay. So this is just the real part. I'm putting the limits. So I'm getting e to the I omega tau plus I omega tau t prime and t, they go away when I'm putting t prime equal t. So I'm getting I omega tau times t divided by tau divided by 1 plus I omega tau. And when I'm putting this minus infinity, this goes to 0. Okay, what is the real part of this guy over here? To understand this, let's multiply both by the conjugated of 1 plus I omega tau. So this will be the real part of ei omega t times 1 minus I omega tau divided by 1 plus I omega tau multiplied by 1 minus I omega tau. And the reason I did it is because this term is going to be real, so I can take it outside. Let's see it. So this is equal to I0 times R times the real part of e to the I omega t times 1 minus I omega tau divided by, what do we have here? So we have 1 plus omega tau to the square. We had a minus sign, but we have also I to the square, so it gives us another minus. Right, so I'm continuing. Okay, I can take outside 1 plus omega tau square. And I need to take the real part of this guy, right? But what is the real part of this guy? E to I omega t, we can write it as cosine and sine. So it will be cosine omega t plus I sine omega t multiplied by 1 minus I omega t, omega tau. All right, so this is just I0R, 1 plus omega tau to the square. And now I need to take So I need to do this multiplication, and I need to take only the real part. First real part that you see is just cosine omega t, right? When I'm multiplying by 1, I can take it outside. Another one is when I'm multiplying omega t with this sign over here, right? So I'm getting getting omega t times the sine omega t. Omega tau, sorry. Okay. So this is clear? This? No, so let's. So it's cosine omega t plus I sine omega t divided by, multiplied by 1 minus omega tau times I. Okay? Okay. Now, here, I can, every time I have cosine plus sine with the same phase, right? I can always write it as, so let's say we have A of cosine omega t plus B sine omega t. I can always write it as some function, some amplitude A times cosine of omega t minus phi, where A is given as a to the square plus b to the square root, and phi is given by tangent phi, which is equal to b divided by a. This is something that is just an identity. It's very easy to show it for yourself. See that you know it. We're going to use it maybe somewhere in the middle of the course again. But every time we have summation of cosine and sine with the same phase, with the same frequency, we can always write it as cosine of omega t minus phi. So you can do the math over here and see that what we get here is I0r divided by square root of 1 plus omega tau to the square multiplied by cosine of omega t minus phi, where phi is, or tangent phi, is just omega tau. All right, so this is v of t when we have cosine input. Let's see how it looks like, okay? First, you see that the input was cosine with amplitude I0r. The output is a cosine with some phase shift, we'll get to it, but with an attenuation of this term. So if we can look at the gain is going to be the amplitude of the input divided by the amplitude of the output. So the gain is R times I0, this is the amplitude of the input, and I'm dividing it by the amplitude of the, So it's usually let's write it. So it's the amplitude of the output divided by the amplitude of the input. And in this case, it is just I0r divided by R divided by square root of 1 plus omega tau to the square. And I need to divide this but by Ri0. So the gain in this case, the gain of the circuit, is 1 divided by square root of 1 plus omega tau to the square. What does it mean? It means that, okay, let's see how it looks like. If this is the gain, and this is omega, or I can also write here the frequency, right? Omega is just 2 pi f, so it's the same. So we see that the gain goes down with the frequency. It means that if we insert cosine input with some frequency which is very high, right, something that oscillates very high, very fast, then the gain is going to be very small. So we are going to see that the amplitude of the voltage is extremely small. If we insert an input with frequency which is very slow, so something that changes very slowly, then we see that the gain is almost close to 1. It means that the fluctuations, that the oscillations are going to be equal to something with modulation of R times I0. This, in other words, is called a low-pass filter. Because we filtered only the low-pass frequencies. We throw away all the high frequencies, right? Because if we insert something with high frequency, the amplitude of the voltage is going to be extremely small. So this is for the gain. What about the phase shift? So we insert cosine omega t, and we got cosine omega t minus some phase. What does it mean, this phase? So it means that if we insert now, so this is v of t. V of t go from Ri0 divided by square root of 1 plus omega tau to the square. And it also oscillates like the input, but with a phase shift. So if we take now a function and we move it by some, we do a translation with phi, it means that this function is just going to move, right? So we have a phase shift that goes, so we don't start from, the maximum is not going to be at 0, it's going to be a little bit shifted, and the function is going to look like this. Okay, so at 1, we go back to this place, right? But the peak, for example, is not at 1 hertz, but at 1 hertz plus some translation. Okay. Any questions about this? Okay, so in the exercise, you see what we're going to do in the exercise is two stuff. We're going to. You have a question? So what you see in the exercise, we're going to do two stuff. First, I'm going to give you another function I of t that you'll need to solve the integral. So all the stuff that we did here very fast at the beginning, you do it by yourself. The second thing that you're going to do, you're going to simulate a differential equation. And for this, let me explain what do I mean by simulating a differential equation. So the second subject that we are going to deal with is how to simulate ordinary differential equations. So I'm going to explain what is the Euler method for numerical integration of first order ordinary differential equation. Right, ODE, it's ordinary differential equation. So in general, these equations, they look like this. We have a function y, all right? And we have the differential equation dy dt, which is equal to some function of y of t, and maybe t also. And I need also to give you, so this is, let's say what it is in a second, but what I need to give you, in order to have a unique solution, I need to give you also what? The initial condition. So this is subject to initial condition. Okay, let's Let us give an example immediately. So for example, we want to simulate dy dt, which is equal to minus a times y of t. Okay, what is f here? F is just minus a times y of t, right? This is just what's written on the right-hand side of the equation. Now, f could be more complicated. For example, so this is, let's call this 1, let's call this 2. And let's give another example. So, for example, dy dt is equal to, I don't know, let's say y of t to the square plus y of t. So this is function of this guy, and it might be also depend on t. So maybe also cosine omega t, maybe also t to the 5. I don't know. Again, this is what we see here. This is equation of this f that we see over here. And we would like to simulate this equation. And why do we want to do it? Because not always we can solve this equation, and sometimes we'll see that we're going to have many neurons. So to solve these equations in many dimensional, it's even harder. So sometimes we would like just to simulate to understand what we have. Okay. So what do we mean by simulating? What we want to do, what do we mean by solving? Let's solve this equation. We know what's the solution, right? This is like putting I equals 0 before. The solution of y of t is just the initial conditions times e to the minus at, right? This is the solution. Now, what we would like to have when we're simulating it is choosing time points, and in each time point we would like to get something that looks like this. So we would like to, so here is how this equation looks like. So it's decaying exponent, so it looks like this. At t equals 0, it starts at y0, and it decays like e to the minus 80. So what we are going to do, we are going to divide time, because in the computer we can only do discrete stuff. So we are going to divide the time to small elements of size h. So this will be t1, which is equal to t0 plus h. And this will be t2, and so on. This will be tn. And we would like to know what is the value of the function at each point. And we are going to do it in an iterative way. So let's see how we do it. Right, so let me remind you what we want. We want to have a list. Given t, t0, t1, tn, we would like to know y at y0, y1 until yn. This is this is our goal. So let's start by estimating. We know already y0. This is given, right? So let's start by estimating y of t at t1. So y of t at t1 is just equal to y of t0 plus h, right? Because t1 is just t0 plus this small infinitesimal small translation. And now let's try to estimate this. We can use a Taylor expansion. If h is very small, we can use a Taylor expansion for this function. So we know already what is y at t0. We just need to add the other terms. So I need to estimate the derivative of y at t equal t0 times delta h, times h plus the times the change. And of course, plus other terms, but this is an estimate only. Now, what is this term? This term we know, right? This is given. What is this term over here? H we determine it. What is this term over here? So I remind you that the only thing that we know about the differential equation we know this function, right? So that we know the derivative of y at t0. It is just the function at t0, right? So it's just the function y at t0, which we know, and t0, which we also know, times h. So this gives us the first estimate for the Euler expansion. The first Euler step in simulating using Euler method. What does it mean? We start over here. We want to know this, but we don't have this. We have only this guy over here, and we have the derivative. This is this tangent over here. So instead of getting this guy, we are getting y0 plus the linear term. We are getting this guy. It means that we have some small error over here. What are we going to do in the next step? So let's estimate y of t at t2. So we're going to do exactly the same. We want to know y of t at equal t2, at equal t equal t2, at t equal t2. We know y at time t1, right? Because we have the estimate for it. And we are going to add for it f of y at t1 times h. So this will be the second Euler step. So we are starting not from this place, we are starting from here, and we again do some steps that might increase even the error that we have. Okay. And this will, from this, you can go to the n Euler step, which is just y of tn is equal to, or let's write it just as yn, which is y at time tn. Okay, y at tn, we define it at yn. This is just equal to y at time n minus 1 plus the function at yn minus 1 at tn minus 1 times h. Okay? And that's it. This is the Euler method. This is how we're going to get estimate for our function at each point. Now the question is going to be how small h should be. Okay? Because if h is too large, this error is going to be bigger and bigger. And maybe we get here a bad estimate for the function. So I'll finish with this. And I finish by giving you an example for what we want, how small we want h to be. So on the one hand, we saw that the solution, so we know the, yes?
Is there a generic estimation for the error, for how fast the error grows?
For what?
For how fast the error grows.
So this will be depend on the function and on the derivative. So we won't go to it, okay? But let me try to show you one example how small we want h to be. And the example is going to be, so remember we know the solution for this, we know the solution for this equation, right? So let's use it. We know that y at time tn is just equal to y0 e minus atn, right? Now, what is tn? Tn is just if we assume that t0 is exactly at 0, tn is just n times h, right? t1 is h, t2 is 2h, and so on. So it means that the real solution is going to be e to the minus a n h. Now we have our estimates, right? We know what's yn here. But this yn depends on yn minus 1. But yn minus 1 depends on yn minus 2, and so on. And we can go, this is called the recursion. We can solve the recursion until we get that yn is equal, and this, just do it, it's exactly 2 lines. Yn is equal to y0 times 1 minus ah to the n. Right? I'm doing it once, I'm doing it twice, and do it n times. It brings me this n over here. Okay? It's in my notes, so you can follow it, but I want to... Okay. So this is the analytical solution. Analytical solution. And this is the Euler estimation. Okay? And the way I got it, again, is by solving this recursion. I'm going 1 step back, I'm getting yn as function of yn minus 1. I'm going 2 steps back, I will get yn as function of yn minus 2. I will go n step back, I will get yn as function of y0 and n, which is what we get here.
How did you get the y as
Okay, let's do it. Okay, this is yn. Yn minus 1 is equal to yn minus 2 plus f to the yn minus 2 tn minus 2h, right? Now let's put our differential equation in this example, where f is just minus a times y of n minus 2, right? So we have these two equations. Yn is equal to yn minus 1 minus a yn minus 1 times h, which is just equal to yn minus 1 y minus ah. And we have that yn minus 1 is equal to yn minus 2 minus a times yn minus 2 times h. So this is yn in our case. This is yn minus 2. Yn minus 1. Right. Combining these two equations, I can get that yn is equal to yn minus 2 multiplied by 1 minus ah to the 2. Right? Now I can go back n step back, and I will get this equation. Okay. Now we want that these two equations will be similar. They are not similar. This depends, of course, on h. But at least we would like to know that in the limit of n goes to infinity, we know that this equation goes to, when n is very large, this equation goes to 0. So at least we would like that this equation will go to 0, right? So we would like that at least in the limit of n goes to infinity, y0 times 1 minus a h to the n will be 0, right? At least this. Because if this is not true, it means that we accumulated error during the way. And this is true if and only if 1 minus ah is smaller than 1, right? Otherwise, this term explodes. And this is true if ah is between 0 to 2, or if ah, or if a and a is positive, okay, a is positive, and h is always positive, it means that a should be smaller than 2 divided, h should be smaller than 2 divided by a, okay? And now just let's finish with the diagram. So here is our analytical solution for y of t. And we start somewhere here. If h is small enough, right? So if h is smaller than 2 to the a, then we're going to do something that looks like this. It might do something like this, but eventually it looks very similar to the analytical solution up to small errors, and in the end it goes to 0. On the other way, if h is bigger than 2 to the a, then these Euler steps are going to be too big, such that eventually we accumulate the error such that at infinity it goes to infinity, not to 0. So this tells you that depending on the function, what we have dy of dt, which equal to some function, depending on this function, we need to take h, which is small. And this is an example. How small h should be? This depends on the problem. But you will see that if you take h, which is too big, you see something which is, and this you see in the exercise, you see something that doesn't look like like the analytical solution. So you need to take h to be smaller and smaller. If you take h to be too small, we have a price that we need to pay, a trade-off, and the simulation will take more time because we need more steps. But in simple equations, in what we do in the computers that we have today, this is negligible. Okay, so this was the Euler method. We did the first order Taylor expansion. We can use more expansions. This is, for example, is called the Runge-Kutta. So you can look at it. We won't do it, but this is the method that most of the people use, the Runge-Kutta 4. It means that we use a fourth order approximation. It's a little bit more complicated to explain, but the rationale is the same. Let's take a break of 15 minutes and see if Jonathan came back. If not, maybe we'll do another. שאין להם רקע מתמטי לפני, ששם זה פחות או יותר רוב הדברים שנלמדים כאן. זה קורס שהוא, אם אתה מכיר את החומר, אז זה לא קשה להיזכר. אבל עדיין הדברים האלה, עדיין עשית אותם פעם ושכחת. לעשות אינטגרלים זה דבר שאתה, זה טכניקה, דברים שצריך לדעת לעשות.
לא התכוונתי לקורס,
אז אני יכול לתת לך לינק לקורס שלהם. אם אתה רוצה, יש להם אולי גם ספר קורס לדעתי.
כן, אני אשמח.
זה קורס באלגברה לינארית לא, אלגברה לינארית זה סוג של חדווה כזה, שזה נגזרות אבל זה בערך מכסה את מה שאנחנו צריכים לקורס הזה.
אוקיי. כי הפעם האחרונה שלקחתי מידע זה לפני 5 שנים.
כן.
טכני.
להבין עקרונות, זה לא קורס רק בשביל להבין עקרונות.
כן, אני יודע.
זה הולך להיות, רוב השיעורים, חוץ מזה, כמה פעמים שיונתן ניתן שיעור עם איזושהי מצגת כדי לתת איזשהו רקע או קונטקסט או משהו כזה, הרוב יהיה דברים מתמטיים. שאלה הדברים הבסיסיים יותר.
אוקיי. אבל יש גם סופר גבולים, אז אנחנו עובדים.
ויש גם את שעת הידע הנוספת, אני מציע לך אותה.
כן, בטח. שאלה, לא הבנתי את הקטע עם ה-F, איך אתה בסוף... כן,
לא התחלתי לעשות את זה, אבל איפה
לא, איך, כאילו עכשיו הגענו לזה, את זה הבנתי, אפשר להמשיך לרדת, אבל איך מפה הגעת לזה?
אז נתתי דוגמה, כן? הדוגמה הייתה, בוא ניקח dy dt שווה למינוס a כפול y. זה דוגמה ל-f של שיצאו.
ואז אם נוצר, אז גם בודקים
בדיוק, אז הצעתי פשוט.
הבנתי.
לא תראה לי לעשות את זה, זה היה קצת...
אוקיי, תודה.
כאילו, מה המטרה של הקורס? נראה לי שמגיע את הידע המתמטי בשביל קורסים יותר מתקדמים של...
לא, זהו. יונתן היה אמור להיות פה לפני, וזה לא הסתדר, ולא היה לנו גם שבוע שעבר. יונתן אמור לפתוח את הקורס, הוא ייתן איזשהו רקע קצת יותר... ייתן את הקונטקסט, ייתן את הכל זה, קצת כמו תרגול, אז...
הוא כאילו נוחת לבד את ההרצאה?
כן, הוא נחת. הוא שם מארצות הברית... אני מקווה שהוא ישן, נראה, הקונטקסט קשה הרבה יותר מפה. אז ניתן את הקונטקסט הקצת יותר. הקונטקסט הוא לעבור, אנחנו עוברים מהסינגל ניורון, הנוירון הבודד, שמתואר במקרה הפסיבי ככה, במקרה היותר מורכב יש הרבה יותר מורכבות. אנחנו עוברים לאט לאט לנוירונים לרשתות, ואז בסופו של דבר דברים שהם קצת יותר high-level, decision making.
איך שזה הקורס, כאילו, איך שזה אמור לראות, עוברים ממעגל ארצי למשהו, לכאילו, לא יודע, במעגלי ארצי או משהו יותר מורכב?
אנחנו עוברים למעגל הארצי, אולי טיפה יותר מורכב, יהיה קצת יותר מעגלי ארצי, אבל זה לא הכיוון. מעבר לזה...
זה לא האסנס?
לא, זה לא האסנס. אבל לא, אוקיי, אולי נפלתי במילים שבחרתי, אבל הקורס בהחלט לא מטרתו לתת לך כלים. הקורס הזה מטרתו להראות לך מה זה תיאורטיקל ניורוסיינס, וכמה שאפשר להכניס בקורס הראשון, זה מה שיהיה פה. זה יהיה תיאוריה של... אני אגיד דברים, אבל זה לא תכיר, זה לא חשוב, אבל תיאוריה של איך, של דינמיקה של רשתות, איך רשתות נראות ביחד, ודברים כמו functions, איך נוצרים נושא של selectivity, כל הדברים, נראה לך נסביר.
היי.
בהקשר לזה, למה הקורס הוא בחירה במדעי המחשב?
אין לי מושג למה הוא בחירה במשהו. למה הוא בחירה במדעי המחשב? הוא בחירה בפיזיקה כי הוא קצת סבור בדברים בפיזיקה. במדעי המחשב, אוקיי, זה לא קורס ב-artificial learning. ואנשים שבאים במדעי המחשב לפעמים זה מה שהם חושבים.
לא, אני לא חושב שזה יכול להיות כאילו, ברשתות אתה יכול, לא יודע, איכשהו, לא יודע, היה לי קורס ברשתות תקשורת, אבל ברשתות נוירונים אולי נשמע.
זה יהיה בעיקר הדינמיקה של הרשתות הנוירונים, ובשליטת, בהמשך הקורס זה יהיה איך זה קשור לאיזושהי פונקציה, למשל איך זה קשור לקבלת החלטות. איך הדינמיקה הזאת של הרשתות של הנוירונים, איך באה לידי ביטוי בקבלת החלטות. למשל באה לידי ביטוי באיזשהו, יצירה של זיכרון. איך הדבר הזה, איך זיכרון מיוצב בצורה קשר של דינמיקה של השם.
מה הספקת?
לא היה את הקטע הרגיל, שאני מרגיש שאתה נורא נורא לאט, ואז מסתבר שזה נורא מהר. בסדר, אנשים שאין להם את ה...
אמרת את מה שרצית?
לא את מה שרציתי חוץ מדבר אחד שזה כמה פלסים שהצליחו לך.
מה?
דילגתי על, כי עשיתי לפני, דילגתי על כמה פלסים שהצליחו לך. איפה אתה יודע את זה כתרגיל, אם אתה רוצה ללמד את זה עכשיו משמע.
נראה כמו בן אדם שרוצה ללמד משהו?
הגעת, הצלחתי.
למה? אמרתי שאני אגיד.
כן, אבל ציפיתי שתשלח לי למילים או...
מה אני אומר?
כן.
כן.
בדרך, חתיכה איתי. בזמן, לחצתי.
לא היה...
לא עצרו אותי על...
התלבטתי, אתה יודע, חשבתי כשהייתי בניו יורק, אמרתי משלח לו אימייל, אם אני מציג לו, הכי גרוע, אז הוא יגיד, אני לא אלמד, זהו.
לא, עכשיו לפחות שנחצתי, תגיד לי, לא עצרו אותי על הסתמך, אבל עצרו אותי לכם, הצלחתי להעביר את כל מה שרציתי.
החבילה, מה הכדורים שביקשת הגיעו. זה מה שרצית לשמוע?
כן. זה
המיקרופון.
מיקרופון, צריך לראות מישהו מקליט. נכון? שזה כזה, אני צריך שזה...
תדבר עם ניר.
נירש?
ניר. זה שלך, נכון? בסדר, יהיה תרגיל, לא דיברנו על התרגיל שמקבלים היום.
כן, זה דומה.
אני רוצה לראות אותו. בסדר?
שני כזאת.
מתי שחררת
לא,
אותם?
סיפורים.
בזמן?
לא, 5 דקות אחרי הזמן.
5 דקות אחרי הזמן?
זה לא עשיתי פוריה.
אולי נעשה
אבל עשיתי, כן עשיתי.
בסדר, טוב.
טוב.
מה שאתה אומר מהמנהל שלכם?
זה ביפן, זה לא...
מה?
זה ביפן.
לא תגמור כמו רוברט. יש לו עבודה נורא יפה. ומה? לא, כבר שנים, הוא לא שולח אותה.
באמת?
כן. אתה יכול לעשות לי טובה להבין? יש לי זמן, אני אגיד לך.
טוב, אתה יודע, אני יש לי דוקטורט הזה, אני יכול לתת משהו נורא אחר.
בדיוק. כל אחד זה, אתה יודע, כל אחד זה... וחוץ מזה...
כן, אבל אני עשיתי שלם על ה...
וגם היה יום הולדת לשתי השותפות שלי.
Did Ran use Potesso? Okay. Well, we will need it. Okay. Good morning, everyone. So we will talk about neural networks, or I think more generally about this. You can consider it as an introductory course in computational neuroscience. The name neural networks is a bit, I guess, to some extent obsolete. Before talking about the science, I'll talk about administrative issues. So, course requirements. When I say requirements, these are requirements from you. First, attendance. So, like every course or most courses in the university, attendance is obligatory. Of course, I will not stand here and check your names, but when I say attendance, what I mean that you need to know everything that has taken place in class. Okay? Either by being here or by taking care of learning whatever there was in class. Homework assignments. There will be one homework assignment every week, or almost every week. And the homework assignment will be composed of an analytical question and a numerical question. Those that took my course in computation and cognition, it's more or less the same idea, and you're required to submit n-1 out of the n assignment. If there will be, I guess that there will not be 14, perhaps there will be 12, something like this, and you have to submit 11 out of 12. There is the course is composed of 3 hours of lecture and 1 hour of exercise. I take the liberty of changing the order. There will be some weeks without an hour with Ran. In other weeks, there will be more than 1 hour with Ran. This will be depending on how I decide where we need more or less hours of TA. In addition to the 4 obligatory hours of the course, there will be 1 extra TA hour. This hour is intended for those that are less comfortable with math, with mathematical tools used in the course, and we will fill it with whatever we think would be helpful to you. But what would be most helpful if you just tell Ran, we need to know, could you give us an hour or 2 hours about this topic that we feel we need extra help with a particular topic. This could be either with something in MATLAB that you want to learn how to do, or it could be something in some mathematical tools that you feel that you need. Just this is there will be nothing new learned in that hour. Basically, it's an hour that is supposed to help you. So it would be most helpful if you send an email to Ran and tell him we want this or we want that. We make an effort to record the class. Basically, those that don't want to show up can watch the video. It doesn't always work very well for technical reasons. I think that it has never happened that we had 100% of successful recordings, so don't count on it. It's for you. It should. We're making an effort, but don't count on it. Eventually, there will be an exam. It will be an open notebooks exam. You'll be able to bring your notes with you. And the final grade is a 70% exam and 30% the grade of the homework assignments. Any questions about that? Yeah. No, there is no textbook. Not only that there is no textbook, I can't even, in most cases, I can't even tell you, read this chapter or that chapter from this or that book. The reason is that the level of the textbooks are either too low or too high for the thing that I teach.
In terms of the exam, is there any restriction on the types of notes that we can bring? Like, can we bring stuff from other people, stuff we printed out, the manner?
If you mean like the notes that your friend wrote, that's fine. If you mean that you want to bring all the volumes of neural computation from 1995 to today, I'm not sure, but we can discuss it. I'm not sure that it will be useful for you. It definitely has to be printed in the sense that you cannot bring your laptop or written or printed, but you cannot, I mean, it's not, if you're concerned about you want to bring the notes of someone else, that's fine. Okay, syllabus. Yeah.
Are there any prerequisites for people that are not versed?
Yes and no. No, in the sense that there are no formal prerequisites. If you study English literature and you think that this is like that neural networks are something that you always wanted to learn, fine, come. But you need the level of the course with respect to math and computational skills is adapted to the level of LSEC students that took all the prerequisite courses in the first semester. So if you are unsure, we can discuss it. If you are unsure whether the level of the course is appropriate for you, we can discuss it after class. Any other questions? Also, you may have noted that I'm speaking English. The course will be given in English. Syllabus. I'm always kind of, I feel awkward presenting the syllabus because you don't know the meaning of most things that are written here. So it doesn't really make sense to tell you that we will talk about the oculomotor integrator if you've never heard about the oculomotor integrator. Well, basically that's the syllabus. If you're interested, the presentation will be online, so you can look at the syllabus. There are two goals. I have two goals in mind when teaching this course. One goal is that you will learn all these things. But a more general or a more important goal is to provide you with the basic analytical and numerical tools that will help you in modeling neural networks in particular and more general cognitive functions. And the focus of this course is on dynamics. The next course, in neural networks B, that is given by Yoram Burak, will focus on other tools more related to coding and information theory. The focus of this course is primarily dynamics. Any questions? So I will start with an example that I know that many of you have already seen it. Those that took, those that have either took other courses or have seen this example. But I find it, I find this example interesting, so those that have already seen it, please don't ruin it for your friends. And I'll show you a short movie, and your goal will be to guess what you see here. Any guesses? It can't be that all of you have seen this movie before.
A mouse moving through a maze.
Mouse in a maze. Other guesses?
Neural network
Neural network solving
solving a maze.
a maze. Well, I think that for sociological reasons, the second possibility seems unlikely, because if it would have been a simulation, the quality of the video would have been higher, right? So it doesn't make much sense that it would be a simulation. Anyone else wants to guess? So these are two examples of trajectories. The color represents time, so this is, I think, the trajectory that you've seen. But there were other examples where there was a somewhat different trajectory. To give you another piece of information, I'll give you the spatial scale. This is 1 centimeter. Here goes your mouse in a maze. Well, maybe it's a very small one. Yeah. So it turns out that this is a boring problem. Well, boring for us, not boring for these people who presented it. These are chemists that are interested in chemotactic droplets. So there's a gradient of a chemical. There's a gradient of a chemical, and you put a droplet, and through the interaction of this droplet with a gradient, the droplet moves and finds its way in the maze. Now, if you're a chemist, of course, you're very interested in the chemical reactions that enable this droplet to find its way in the maze. But if you're a neuroscientist, well, you shouldn't be that much interested, because it's all chemical reactions. Nevertheless, well, at least one of you thought that it could have been a mouse could have represented a mouse in a maze, in the sense that, well, it seemed like something intelligent that was solving a problem, or maybe a neural network if you're, I don't know, a computer scientist or something like that. And I think that the lesson to learn here, there's a lesson to learn here, and here you see this droplet moving in the maze. Now, the lesson I think to learn here is that it could be the case that what seems like a complex computation can be understood using simple principles. It gives us hope that when we study behavior, when we study even complex behavior, maybe there are simple underlying mechanisms or underlying computation that we can find, as there are here in the example of the droplet in the maze. And our goal, I think, as people who study computational neuroscience, is to identify these simple and basic mechanisms. So there's hope, maybe, to understand the brain. The basic the basic element in the brain is the neuron. What you see here is a beautiful picture of a region that's called the dendrite gyrus. All these beautiful colors are each and every one of them is a neuron. that was, I will not go into the technique, but there's a technique, it's called, the name that it was termed rainbow, which enables to have different colors from different neurons, and we are studying these basic elements. This is another brain structure using a different technique. This is brain structure that I particularly like. It's called the cerebellum. It sits here. It's maybe important for motor control and motor learning. You see these beautiful Purkinje cells. And we will, in the course, we will have, we'll use many simplifications and approximations, but I think that it's important to bear in mind that things are much more complicated than that. I want to show you an example of how things really look like at the microscopic level. So what you see here is a very small part of the mouse retina, and this is, maybe I'll say a few words about the technique. So the technique here is to use electron microscopy to reconstruct small pieces of the brain, and this is basically how it looks like when okay, I'll have to explain more. So you take a small piece of the brain, you fixate it, and then you start cutting very, very thin slices, and you image each of these slices. This is not exactly what they've done here, but for the sake of argument, it's good enough. And from this, they try to reconstruct cells and the connections between cells, and what you'll see here is it's called the connectome of the mouse retina. This will give you a feeling of how things look like in the brain. So these are the cell bodies. And what you'll see here is focusing on one of these cells and looking at the connections, building the connections between the different cells. So this is one cell, and it's neurites, and you have many such cells, and this is how they are connected in the retina. Now our goal is to try and understand what's going on, how computations are achieved in such a structure. Now the retina is a simple structure. You see the different layers of different the different layers in the retina. The retina is easy because it's structured, because we know it's in the periphery, so we know the input to the retina. Everything is easy in the retina, but still. This is what we need to understand. Each one is a different neuron, and you have different neuron types. So when you see here, they worked very hard to color different neurons using different colors. So there are no empty spaces in this part of the brain. It's all filled. This is reconstruction of one neurite of one neuron. This is how it looks like. Now, to give you numbers, we have something like 10 to the 11 neurons in the brain, connected by something like 10 to the 14 synapses. This is what we need to understand. We know very little about the connectivity. We know more about the activity. at least connectivity at the microscopic scale. These are first attempts to do it. This is work, I think, from last year. This is a connection between, this is putative synapse, a connection between two neurons. As I said, we have 10 to the 14 such connections. And this, I don't know what's it. Oh, okay. This is, from this very simple, from this study, what they've constructed is a connectivity matrix of something like 700 neurons. So basically, each color here corresponds to the connection between two neurons in this small brain tissue. So it represents a connectivity. This is the guy that did it. They don't have too much information about the strength of a connection. In principle, you may be able, using this technique, to gain some information about the strength of a connection. What you see here is the connectivity between these 700 neurons. So it's a 700 by 700 matrix, and they are sorted according to neuron types. There are many neuron types in the retina. So this tells you something about the complexity. So this is 700 by 700. In principle, what we are interested in is 10 to the 11 by 10 to the 11. That's our goal. Look at these synapses. Even storing this information, I don't know how is a challenge. So this is a real neural network, if you like. So that's the complexity of the things that we will have to address. So I think that the first question that one needs to ask when studying the brain, when studying cognitive processes, is what is the right level of abstraction? I mean, why do we talk about neurons at all? Why not start with atoms or quarks or molecules or brain regions? I mean, if you open a psychology textbook, they will tell you, for example, that the premotor cortex plans movements. This planning goes to the motor cortex, and the motor cortex generates the required movement. So perhaps the proper level of abstraction, the right level to study the brain, is thinking about large regions of a few square millimeters or even a few square centimeters and how they interact, rather than talking about neurons. Now, in the 19th century, the dominant view was actually that neurons are not very important because the brain is like a big mesh of connected cells. So there's like when thinking about the brain, it's a mesh network. There are no discrete elements, and these were the supporters, big supporters of this theory. Some of you may have heard the name Golgi. He won the Nobel Prize in physiology for developing a very nice technique of staining neurons. There are neurons that bear his name, Golgi neurons. And on the other side, there were people like this guy that I can't even pronounce his name, and Ramon y Cajal, I'm sure that many of you have heard his name, that argued, I'm sorry? Oh my God. So there are two possibilities, right? One is that they were twin brothers. That's one possibility, identical twins, right? Or that I made a mistake. Now, since I never make mistakes, it is probably that they were twin brothers, but how do you know that they were not twin brothers? I'm sorry? You can change your name. That's not an issue. They were not born at the same year. Okay, so maybe the... Okay. Yeah, they were twin brothers, but I don't know how it happened. I'm trying to think of a mechanism. They were the mother of these two gentlemen had the fertility treatment, and they took. Okay, maybe I'll change the picture. Okay, so they argued that the brain is actually composed of individual units that are do not actually touch each other, and that neurons in the brain are cells like in all other tissues in the brain. And the nerve fibers that people saw at the time are actually cell processes. And these cells are connected at sites of contact, but there's no continuity. And of course, we know today that they were right. And the basic element in the brain, or that's the common view, is the neuron. Now, this is how neurons look like, or at least this is how neurons looked like using the techniques of the time of Ramon y Cajal. These are drawings of Ramon y Cajal using the Golgi staining technique. In our model, all our models that we will consider in this course that's how we will think about the neuron as a point. Now, you could argue that, well, it's not a very good description of what's going on. Now, in computational neuroscience, some people do use or take into account the shape, the anatomical structure of the neuron. We will not do it in this course. And in many models of the nervous system, we do this. We use this approximation of thinking about the neuron as a point. This is very useful when we need to model a brain with 10 to the 11 neurons. But you can immediately understand that there are advantages but also disadvantages of this description. So we have to bear in mind that this is how our models look, and this is how the real brain looks like. So our basic element is the neuron. Now, neurons are electrically active. There's electricity in the brain, there's electricity in neurons, and what you see here is an example of an experiment by Luigi Galvani. You see that it's a different person from Ramon y Cajal and Golgi. And what you see here is rather difficult to see, but this is a frog, and it's wired. There's a wire here going up, and the hope is that at some point a lightning would strike, and this would activate the. I think that it's only a leg of a frog. I'm not sure whether it's a whole frog, and he was doing experiments with animals and with electricity, and it turns out that our understanding of electricity and our understanding of electricity in the nervous system or in biological systems went together for several centuries. There were long discussions whether the electricity in animals or in organs is the same as the electricity that you see in non-living physical systems, and these experiments, and similar experiments reveal that in fact we are talking about the same things. So what do we mean by saying that neurons are electrically active? What you see here is a recording from a Purkinje cell in vivo. This is a recording from the brain of an anesthetized rat. And the idea is that you take a microelectrode, you put it inside the neuron, and you record the membrane potential, the difference in potential between the inner side and the outer side of the neuron. This is how recording in Purkinje cells look like. So this is a Purkinje cell. This is another drawing of Ramon y Cajal. And you put an electrode. Well, you don't see it when you do the experiment, but you think that you put the electrode either here or in the proximal part of the dendrite, but hopefully it's in the soma. You will not be able to put your electrode here. It's much more difficult. So you put your electrode here, and you look at the membrane potential, and you see that it's changing with time. The order of magnitude is changing from, let's say, minus 60 millivolts plus to, this could be perhaps 40 millivolts. So the neurons are electrically active. Now the first question is, why are neurons electrically active at all? Why should there be a potential in neurons at all? Any ideas? I'm sorry? No, I'm not. This is not. I'm not asking a computational question. I'm not asking what is it good for. I'm asking why. So ions. So we can think about a neuron as a bag of ions, or well, bag of water. So we have it's like a sphere filled with water, living in a aqueous medium, and there is a difference in the concentration of different ions. There's a difference between the concentration inside and outside. And since this is the membrane is composed of lipids, ions and water cannot easily go from the inner side of the cell to the outer side of the cell, and vice versa. So there is a difference in the concentrations of different ions between the inner part of the cell and the outer part of the cell. The sizes here correspond to the concentration of different ions. For our purpose, there is a lot of potassium inside the cell and compared to the outer side of the cell, and there's a lot of sodium outside compared to the outside the cell compared to the inner part of the cell.
What's A?
Other. A corresponds to other. No, it's not a new element, if you were wondering. Okay. So why would a difference in the concentration of different ions lead to electrical activity? Yes? Why should there be a potential here? Okay, so, well, if the cell is, if you have a membrane and nothing going out and nothing is coming in, then no one, well, I don't know, there will be no potential. Okay, so what would happen if there's a channel? Okay, so if you open a hole here, potassium would go out and sodium would go in. Why would it generate a potential? Okay, so I open a hole, potassium goes out, sodium goes in, and the cell somehow, there are pumps that I'm sorry? I'm sorry? I can't hear you.
Changes in state, I guess, right? In activity during the neuron life. So I guess physical states also must change.
I don't know what you mean by physical state.
It's not something static, right? The neuron does something in its life, in its life. So I guess the change in the cycle of its life requires physical changes.
But I mean, it's too vague to answer the question. What are the mechanisms for? electrical activity. And it turns out that the answer is pretty simple. And it has to do with the fact that there are conductances, but what is important about these conductances is that they are specific conductances. So ionic channels, ionic channels have a specificity in them. What is the key word here is specificity. If you just take a bag or a cell with where there's a difference in the concentration of ions in the inside and the outside, and you make a small hole, there will not be any electrical activity. At the heart of the electrical activity of the cell is the fact that there are specific conductances. For example, there are ionic channels in which potassium ions can flow, but not sodium ions. So what are the implications? Well, the concentration of near this channel, the concentration of potassium in the inner part of the cell is higher than the concentration of potassium in the outer part of the cell. And therefore, there's more flow of potassium in this direction than there is in the other direction. Yes?
What is the mechanism for allowing potassium to go out but not sodium?
Just the channel itself. It's not just a hole. There's a difference in the size of the ion. There are differences in the ions. They differ in the chemical interaction. So the important thing here is that the channels are specific. Many channels are specific. So because of diffusion, there will be more diffusion outside from the inner part of the cell to the outer part of the cell than there will be diffusion from the outer part of the cell to the inner part of the cell. And as a result, there will be a small change in the overall electrical charge. So you'll have an accumulation of positive electrical charges on the outer part of the membrane and accumulation of negative electrical charges on the inner part of the membrane. And this is the mechanism. This lies at the heart of the fact that cells are electrically active. There are different processes in the cell that change, that open and close these specific conductances, and this opening and closing of these specific conductances results in change in the potential or of the membrane of these cells. Now, if you want to be more quantitative about it, we can note that each ion can be either in the outer part of the cell or in the inner part of the cell, and we can look at the energy that is associated with these two states. So what determines this energy that is associated with these two states are three things. One is the valence of the ion, how many electrons it is missing or how many extra electrons it has, the charge of the electron, and the potential. So the energy associated with an ion outside will be equal to the product of the valence with the electron charge with the potential outside. And similarly, we can, in an identical way, we can compute the energy that is associated with an ion being inside. And we know that the steady state distribution, the Boltzmann distribution, in this case would be that the ratio of the concentrations outside and inside will be equal to e to the minus the energy divided by kT. And from this we can extract an equation that relates the potential of the membrane potential associated with this particular ionic with this particular ion, given the difference in the concentrations in the concentration of these ions.
The E's in these equations are Euler's number or the electron charge?
I'm sorry?
The
charge of the electron.
Okay. Is that a constant for every electron, or is it different?
Charge of the electron is a
Oh, it's just plus or minus.
no, I don't remember the number, but it's a universal constant, the charge of the electron.
Okay, it's in coulombs or something.
So at the bottom, two different e's in the same equation? No, on the left. The one is
This is this is a E, the
Euler's constant.
no, it's not. No, it's a natural E. It's not E. Well, you all know what E is, right? So this is the potential. It's called the Nernst potential. This is a potential that is associated with one specific conductance of one resulting from one type of from the difference in the concentration of one ionic type, and but the life of a cell is more complicated because there are many different ions, and the more important ones for the sake of our discussion is sodium and potassium. And as I told you, there is more sodium outside than there is inside, and there is more potassium inside than there is outside, and the potential associated with sodium is approximately 60 millivolts, and the potential associated with the Nernst potential associated with potassium is on the order of minus 70 millivolts, just to give you the numbers. So the way to think about the fact that neurons are electrically active is the following. So we have the membrane. This is the membrane. And we have the inner side of the cell, and we have the outer side of the cell. And the membrane has several electrical properties that are associated with what you've discussed with Ran this morning. So one thing is that there is a Nernst potential that is generated by the fact that there are differences in the concentrations of different ions, and this is depicted here as batteries. You have conductances of different types. There are conductances that are specific. That are the conductances that are specific to specific ions, and there are conductances that are general, where different types of ions can flow. And also there is capacitance of the cell. So the way that we write, if you like, the equivalent electrical circuit of the neuron looks something like this. So we have capacitance. This is the capacitance of the membrane. We have the different conductances, and we have different batteries that are associated with the different ionic channels. And what is different, or the main difference between the electrical circuit that Ran discussed this morning and the electrical circuit of the neuron is the fact that these conductances can change over time, or as a result of different stimuli. And as a result, the cell has these interesting properties that we saw here. The fact that membrane potential can change. Any questions? So we will take a break, and after the break we will discuss how these things emerge.
לבטל את המסלול ולראות האם מה שאנחנו רואים במבחנים ההתנהגותיים שלנו, של הפסקה של המסלול ופגיעה בו, האם אנחנו יכולים לעשות במקביל גם מודלים חישוביים שיכולים לעזור לזה.
מודלים חישוביים, מה הכוונה?
הידע שלי בתחום הוא... אני באתי לראות האם אני...
מודל יש לו מטרה.
כן.
מה אתה רוצה שהמודל הזה ייתן לך?
שהוא יוכל לצפות את ההפרעות תנועה שאנחנו...
ההפרעות ההתנהגותיות.
כן. ואני באתי לשאול האם... אתה חושב שזה קורס שמתאים?
לא נושא
כן.
האם זה מתאים? זה הקורס היחיד שבו אתה יכול ללמוד לעשות גידול.
איך עשית את זה?
עשיתי פה עשיתי לי.
אוכל? אז זה בטח מושג כזה, כי אנחנו בטח נשאר לפה עד...
בכדור הנחתי את זה. הכנתי לי כזה בלי כלום, ואז עשיתי לי סלט עוף היום.
סלט עוף?
מי אמר שנעביר?
אני לא יודעת, יש לו 5 דקות. אז היא עושה לי אוכל, שלא תשאול אותך לחמם.
אני מבינה אותך, תודה.
איפה הוא משתנה כל הזמן? לאנשים באמת שאין שינוי דומים, מדעי המוח עדיין היו עושים רק אלקטרופיזיולוגיה וליאם.
רציתי לשאול אותך לגבי הדרישות דם שלך.
מה האימא שלך?
BAR ו-TH. אתה תראה.
BAR?
BAR UTH נקודה HAINSON והמדע האוניברסיטאי שטודל אודי מאוניברסיטת מרסי.
אודי נתנאל?
נקודה נקודה כיף למצוא. הסיפור שלי סגרתם שאנחנו מנסים לראות איך אנחנו מנסים למה לא מסובך מדע אפשר להתחיל לנהלים
תגיד, מה זה עניין? זה בעיות חישוביות? זה סיפור במשפט?
תודה רבה.
כן, ואני חשבתי שזה בתור ביולוגיה חישובית.
מה זה תואר ראשון?
משהו מחשב ביולוגיה חישובית. ורציתי לדעת כאילו איזה דרישות יש לידע, כאילו.
דרישות זה...
רוב הזמן הייתי
צריכה לדעת לתכנת. רוב האנשים מתכנתים במחשב. דרישות צריך לדעת קצת אינפי, קצת אלגברימי.
הרבה תרגיל, הרבה תלמידים.
קשה לי, תוכל לתקר
סילבוס. וההתמקדות של הקורס היא אני באתי מראש חשבתי שזה קורס כאילו בלמידה באמצעות רשתות נוירונים.
לא.
זה לא זה.
זה לא קורס למידה באמצעות רשתות נוירונים. הקורס השני קצת בהקשר, במובן של אפליקציות של מדעי המחשב,
לא, ממש לא.
למה זה יכול להיות אינטואיציה, אבל בדיוק ללמידה כזאת? אולי כל מיני, אתה יודע, זה לא באמת, אפילו המודלים הפיזיקים האלה.
כאילו זה עדיין נשמע מעניין, כזה רוצה להבין.
כמה זה יכול לתת, כאילו לא כלים אלא יותר איזושהי ראייה כזאת, שיכולה אולי לעזור לתהליך, לבנות כל מיני מודלים של למידה.
או שיש קורס אחר שכאילו יותר מתמקד או יש קורס כזה באוניברסיטה.
יש כמה קורסים, יש קודם כל קורס ההמשך של הקורס הזה, הוא
קורס המשך בסמסטר הבא.
בסמסטר הבא, נוגע יותר בקידוד, ברשתות נוירונים, זה קורס יותר של דינמיקה.
לא מסתכלים פה על איזשהם אובייקטים כמותיים ומנסים להבין איך הם עובדים, או שזה יותר ברמה דסקריפטיבית.
מסתכלים להבין איך המוח עושה דברים.
בקורס, לא בכלל.
אני אומר בקורס, מסתכלים איך המוח, רוצים להבין איך המוח עושה דברים.
מבחינה פיזיולוגית כאילו בעיקר?
לא, מתמטיקה.
לא, הדגש.
הדגש הוא דינמיקה, השאלה היא מה רמת האבסטרקציה. היום אנחנו מדברים על, ככל שאנחנו נתקדם בקורס, האבסטרקציה, אנחנו נסתכל אובייקטים יותר ויותר אבסטרקטיים. היום אני מדבר על פוטנציאלי פעולה ושינוי במתח חשמלי של התאים, ובאיזשהו שלב נעבור לדבר על תאים כאובייקט בינארי. אחרי זה נדבר כבר לא על תאים בודדים, אלא על רשתות של תאים. רמת האבסטרקציה היא לשאלה שאנחנו שואלים. זה לא קורס בלמידה במובן של לשלם מס שפתיים לביולוגיה ואז לדבר על אלגוריתמים. זה לא קורס על לנסות להבין את המוח, לא לנסות להשתמש בו. האם זה נותן אינטואיציה או לא נותן אינטואיציה? אני לא יודע.
אינטואיציה לא משנה אם אתה תציד, אף פעם לא יגיע לרמה קרובה.
יש אנשים שכן, יש אנשים שמסתכלים על מערכת הראייה בצורה מאוד רצינית, משתמשים בשביל כבסיס למערכות של ראייה מורכבת. יש אנשים, אפילו יש עכשיו חברה שמתעסקת בנוירונים ספייקים, שעושה נוהגים עם אפליקציות למדעי המחשב. שכחתי איך נקרא, מישהו בשם זיקביץ', שבונים הארדוור בעצם של נוירונים בלי פוטנציאלי פעולה כדי לעשות חישובים. האם הם הצליחו או לא? אני לא יודע.
יש עדיין מה, היינו שומעים עליהם.
כל ה-deep learning זה בעצם מאוד קשור לאלגוריתם של back propagation, של הרעיון. לא יודע מה להגיד לכם. המטרה שלי להבין את המוח.
לי אישית זה די נשמע ממש מעניין, אני עדיין רוצה לדעת את זה, אבל...
אני יכול לשלוח לכם את הסילבוס של שנה שעברה. תראו אם זה מעניין אתכם. כאילו, יותר בפירוט. אוקיי?
כן, נשמח.
אבל אל תקפיצו את זה, לא אני כתבתי את זה.
פעמיים M, A-N-E-D-I-T-Z, שטודל,
IGOR נקודה LAP SHUM שטודל מייל עוזי לא ראיתי. צריך יכולה להבין, לא משנה, רמת המורכבות ועבודה של...
רגע, כל זה אבסטרקציה, כל דבר שאתה עושה את זה לאיזשהו מודל, אז זה כאילו אבסטרקציה, אתה לא יכול לעשות מדע בלי לעשות אבסטרקציה.
אני מדבר על בדיוק הפוך, לי, זה נכון בעצם, פשוט יותר מורכב. לפתור
Okay, I found out that Golgi and Ramoni Cajal were not identical twins, and in the presentation that I will upload, you will be able to see the difference, in case you were wondering. Was Golgi? No, this was Golgi. Okay, so now I will briefly show you how we move from the biology to the RC circuit that Ran discussed in the morning, and this will be brief, and then we will move on to understanding these jumps in the Merman potential that we saw in the picture. These also known as action potentials. So the topic is passive response of neurons. Now, before I start, in the break, some people ask me questions that can be understood or related to the question of level of abstraction. So today, and perhaps next week, we will talk about the electrical activity of single neurons. And as the course will progress, we will move to more abstract systems, and at some point we'll talk about neurons as almost binary entities, and then we will talk about networks and large populations of neurons. So the philosophy is that different questions require different levels of abstraction, but the same mathematical tools that can be used in order to understand the dynamics of single neurons can also be used in order to understand the dynamics of large networks of neurons. So what is important? Well, there are two things. One is to understand the different phenomena that we try to understand, but also to see how we move from the biology to the math and back. So we are talking about modeling a neuron. So this will be the outer part, and this would be the inner part. And basically, what we're interested in is the membrane. So the equivalent electrical circuit has a capacitor and has a conductance and the battery. So we will call the potential of the battery V rest, and here we have a resistor whose we can talk about resistance or 1 over conductance. And if we have some current flowing from the outside to the inside, it has two components. One component is the capacitance current, IC, and one component which we will denote as IR is the current that flows through this conductance. So the capacitance current is simply the conductance of the membrane times the temporal derivative of the membrane potential, and the current that flows through the resistor is simply the membrane potential minus the battery potential divided by the resistor, or equivalently the membrane potential minus the battery potential times the conductance. And the total current is just the sum of these two currents, which is equal to C dV dt plus G times Vm minus V rest.
I just want to get some intuition about the relationship of the circuit model to the membrane. So are is the membrane both the resistor and the capacitor? In other words, it has resistance properties and capacitance properties?
Yeah.
So we're modeling this as a resistor and capacitor in parallel, right? That's what's going on here?
There is current that will flow from the outside to the inside, and there is charge that will be accumulated along the membrane, which this is a capacitance.
So, but the current goes through channels, right? Or is this current is this a channel or is this the closed membrane?
This is the channel.
So the resistor is the channel.
Yeah.
And the capacitor is the membrane, the part of the membrane that's not the channel?
Yeah.
So the resistor and capacitor are different things.
Or different parts of the membrane, if you like.
Okay. So
they're all the membrane.
Okay.
Let me change here the notations. I'll call it Vm, the membrane the voltage of the membrane. I'll call it Vm. Now I'm going to define V to be the difference between the membrane potential and the resting potential. So the total current would be just equal to C dV dt plus G times V. And this is, I think, something that you have already seen. Oh, another way of rewriting this equation is tau dV dt is equal to minus V plus I of t times R, where tau is equal to R times C. So there's one one thing that I want to emphasize here. Yeah.
You mentioned before that certain ion routes can be open or closed.
This is just everything is not changing. Everything is stationary. If you'd like to model ions ionic channels that open and close, and we will do it later today, you'll need to add some kind of either, if you want to change or just to be time dependent, then you'll have to add here dependence of G over time. If you want it to be dependent on something else, then you'll have to add this. Basically, this will be a changing G. Now, what I've shown you here is a case where I have only one only one conductance, only one battery. In general, you will have many of these, but since if they are not changing, you can just it can be rewritten as one conductance and one battery, where the battery is a combination of all these conductances. So that's where we are now. Going back to your question of what is it in the membrane that generates these things. So let's talk about the capacitance. So the capacitance is a property of the membrane. For example, how wide it is. But it's also a property of the total surface area. So the larger the surface area of the cell, the larger is the capacitance. So the capacitance, bless you, capacitance is proportional to the total surface area. So the larger a cell is, the larger its capacitance. What about the resistance? Let's not talk about the resistance. Let's talk about the conductance, 1 over the resistance. How does the resistance, or how does the conductance change with the surface area of the cell? So if the cell is homogeneous, then the larger the surface area is, the more space there is for these channels for which current can flow. So the conductance of a cell is also proportional to the total surface area. And as a result, the product R dot C is independent of the surface area. Now, as I'm sure one told you, this tau represents the time it takes the membrane to respond to current or to decay to the steady state of the network. Now it turns out that because conductance is proportional to the total area, surface area, and capacitance is proportional to the total surface area, the product of R times C is independent of the total surface area, which means that small and large cells respond in somewhat similar way to current that is injected to them. Now if we want to put in numbers, some numbers, now in computational neuroscience, it's often the case that people don't pay much attention to the numbers that represent the brain and the neural circuitry. But I think that it's important to remember that behind the math, behind the models, are physical systems, and we need to understand what are the limitations, what are the different time constants. Now the capacitance of a cell, or more specifically the specific capacitance, the capacitance per area, the specific capacitance is approximately equal to 1 microfarad per square centimeter. And the specific conductance is approximately equal to 0.1 to 0.01 millisiemens per square centimeter, and as a result, tau, the time constant of a cell, is something like 10 to 100 milliseconds. And this is true for cells of different sizes, and cells vary in their size. The radius of the soma ranges from The radius of the soma ranges from something like 4 microns to 100 microns. Radius of the soma ranges from something like 4 micrometers to 100 micrometers. So the surface area ranges from what? 4 pi, something like 160 square micrometers to 400 times larger. So cells vary very much in their size, but their time constant is remained at approximately 10 to 100 milliseconds. Any questions about that? Tau is R times C. 1 over G. One of the resistance is 1 over the conductance.
Okay, but also the specific conductance?
So we know that if you want to compute the capacitance of the cell, compute the surface area and multiply it by this number. If you want to compute the conductance of the cell, take the conductance per surface area. This is more variable than this one. This one is pretty constant. This is more variable. Take this, compute it, multiply it by the surface area. This would give you the total conductance. 1 over this would be the resistance. And multiply resistance with conductance, you'll get the time constant. Now note that the area, you have the area in the numerator and denominator, they cancel out. But this is the conductance. When we're interested, the tau is a function of the resistance. More questions? So this is the math. This is the data. What you see here is recording from a single cell, membrane potential of a single cell in the primary visual cortex of an anesthetized cat. And one thing that is obvious is that, well, this is membrane potential. It fluctuates around minus 60 millivolts, and this was easy to understand given the simple RC circuit that we described previously. But you have these events, and these events are called action potentials. And our goal is to try and figure out what generates these events. And these are very important. These events that are called action potential are very important. First, you see them almost everywhere in the nervous system of vertebrates. In vertebrates, there are also other things. But almost all neurons in the nervous system of vertebrates show these stereotypic jumps in the membrane potential. And as the cell is the basic computational unit in the brain, we think that these action potentials are the basic unit of communication. These are very stereotypic events, and when cells talk to each other, it is generally the case, not always, but generally the case, that the only thing that one cell knows about, one neuron knows about what's going on to other neurons in the network is the timing of these action potentials. So if we take two neurons in the network, then the two neurons that are connected in the network, these events are information that is transmitted to the next cell, to the postsynaptic cell, but not these fluctuations. So the action potential is the basic computational unit of the brain. It's very stereotypic. It's very similar in different cells, and it's the only transmittable information. So this lies at the heart of the computation that the brain does, and what we will do soon is try and understand what generates these action potentials. So here you see an example of action potentials of a Golgi cell in response to different injections of cells, of currents. If we look at different cells in the brain, we see slightly different. The shape of the action potential is slightly different. This is an action potential of a Purkinje cell. This is a CA1 pyramidal neuron, a dopaminergic neuron. There are some differences in the width of the action potential between different neurons. There is some difference in what happens slightly after the action potential, this hyperpolarization. So there are some differences between neurons, but we will ignore them. From the point of view of an experimentalist that measures the activity of neurons in the brain, these action potentials are the only thing that we as an experimenter for most experimental techniques, the action potential is the only thing that we know as an experimentalist that's looking from the outside about the neuron. It's almost the only thing that we know about this neuron. So we can put an electrode very close to a neuron, and whenever the neuron fires an action potential, we will have a signal that we can measure, but we will not be able to tell anything about these small changes unless we use intracellular recording techniques, which are much more complicated. So it's not only that from the point of view of the brain, the computing machine, the action potential is the fundamental unit of information transfer. It's also from the point of view of us as people who study the brain and measure the activity of the brain. In most cases, the only thing that we know about neurons is the timing of these stereotypic events, the timing of these action potentials. So it's they are very important in understanding the brain. Now, these action potentials have this property of something like an all or none. If we inject current to a cell and the amount of current that we inject is not sufficient, we'll get a small depolarization, and once we stop the current injection, there will be hyperpolarization. And this is not exactly what you would expect from an RC circuit, but not very different from what we from the behavior of a passive membrane as discussed by Eran. But if the amount of current injected is above some threshold, then suddenly there's an explosion. There's a huge increase in the membrane potential, followed by something like after perhaps half a millisecond, up to 2, maybe 4 milliseconds, depending on the cell type, resulting in a hyperpolarization period that is called after hyperpolarization until the cell gets back to its resting potential. So by and large, these action potentials that we see are an all or none event. If the current injected is below some threshold, the membrane behaves as if the cell is passive. If it's above some threshold, we get these huge and fast increase in the membrane potential, followed by a fast hyperpolarization. One of the successes of computational neuroscience was our understanding of the mechanism or the mechanisms that generate these action potentials. The success was so, in fact, most people no longer care to study action potentials and the differences in action potentials between different neurons because basically everything is solved. And not everyone will agree with this view, but definitely people who are doing theory are no longer very much interested in these action potentials because, well, we basically understand everything. And the people behind our understanding of the action potential are these two gentlemen. As you can see, they are not twins. This is Ellen Hodgkin, and this is Andrew Huxley. And by combining experiments and theoretical modeling, they figured out the mechanism underlying the action potential. This is you see that celebrating the work of Hodgkin and Huxley, they put in 4 figures. The 2 gentlemen that were behind it, they received the Nobel Prize in physiology, I don't remember when, many years ago. These the results and the machine that helped them do the calculation. So this is Hodgkin and Huxley. So what did they do? So they studied this squid, a non-kosher animal, that besides being non-kosher, it has a giant axon that transmits information to the motor neurons that enable the animal to construct these, I don't know how to call them. Sorry? Tentacles? Yeah, maybe. So this animal contracts these tentacles, and this generates basically it pushes water in this direction, and then the animal can go in that direction. And there's a pretty large axon that transmits information to these tentacles, and it is so large that one can put an axial electrode through it. So they had a great experimental system that enabled them to study action potential that propagate in this axon, and these are these. This is a measurement of one action potential going from minus 50 or something like this to plus 40, and you can immediately see this. You can immediately see that this action potential is not very different from these action potentials that we see in our sophisticated brains, we as mammals. Anyone knows what this is? No. So these experiments were done in the 30s, the 1930s. And they didn't have any computers. So this is the idea is that you generate a sinusoidal current of a known frequency, and then when you take the photo, you can this is a way of identifying the time scale of the event. Okay. Smart. They were smart, but that's how people did in the times before the time of computers. Okay, so the model of the action potential as generated as discovered by Hodgkin and Huxley is the following model. So as I plotted before, there is an outside current, a current that can go from the outside to the inside of a cell. There is capacitance, and they considered 3 currents. One is a sodium current, one is a potassium current, and one is a general non-specific current, which they called a leak current. And the equations that characterize the dynamics of this cell are the following. So the change in the measurement potential of the cell, the function of time, is equal to the current that is injected to the cell, minus the leak current, minus the potassium current, minus the sodium current. And to be more precise, I should have added also time dependence of all these currents. And what I will do now, I will explain the properties of all of these leak, potassium, and sodium currents, and show you how the properties of these currents can generate an action potential. So the first current is the simplest current. This is the leak current. The leak current is equal to the leak conductance times the difference between the membrane potential and the leak battery. So that's the first current in the model. The second current is a potassium current. Similarly, it's composed of potassium conductance times the difference between the membrane potential and the potassium conductance. And the sodium current is just equal to the sodium conductance times the difference between the membrane potential and the sodium battery.
So when you say sodium battery, what do you mean?
This is the Nernst potential that we discussed in the previous hour. But what is different between this model and the simple model that Ran was showing you is that these conductances, the sodium and potassium conductances, can change. So the potassium conductance is a product of two terms. One is a global conductance, global potassium conductance, which can be thought of as the number of potassium channels times the conductance of each one of them, so the maximal conductance of each one of them, times a term which they called n to the power of 4, which models the extent or the number of a fraction of channels that are in fact open. And they have a microscopic model explaining what this n is, but I will not have time to explain how you go from the physiology of individual channels to this term n. Now this term n has some interesting dynamics. It changes as a function of time, and this change changes to a value which depends on the membrane potential in the following way. So what you see here is a value of n infinity as a function of the membrane potential. And the idea is that if the membrane potential is very low, let's say at minus 70, n infinity is very low, so the value of n converges to n infinity, and as a result, n to the power of 4 is close to 0, and as a result, there's almost no potassium conductance. On the other hand, if the membrane potential is very high, then the dynamics will converge to a high value of n, and as a result, n to the power of 4 will be large, and as a result, the potassium current will be large. There is also dependence of the time of this convergence to n infinity. This time also depends on the membrane potential. This is shown here, but we will not discuss it. You will simulate these equations in your homework assignments. There is also interesting dynamics of the sodium conductance. So the sodium conductance is a product of three terms. This is a GNA, which is a maximal possible sodium conductance. It corresponds to the number of sodium channels in the membrane times the maximal conductance of each one of them, and two terms, m to the power of 3 and h, where there is a dynamics of m. M also converges to m infinity with a time constant of tau m, where m infinity has similar properties of n, which means that m infinity is large when the membrane potential is high and is small when the membrane potential is low. And the third term is a gating term h, which has the opposite properties. It converges to h infinity, which is open when the membrane potential is low and closed when the membrane potential is high. And simulating these equations, they were able to reconstruct the Mermet potential. Now I know that it's kind of boring looking at all these equations with all these details. And what we will do, we'll not have time to do it today. What we will do in the next week, we will study a simpler model for something that looks like an action potential that allows us to both to gain more insight and also to solve things analytically. Yes. It's a function of the Mermet potential. Yes, and that allowed me to explain how an action potential is generated, here. So let's say that we take, a neuron and put it in something like -70. We keep it in -70. So M infinity is close to 0, N infinity is close to 0, H infinity is close to 1. So the values of M, N, and H will converge to something like 0 for the M and N, and something like 1 for H. Now, the sodium conductance will be close to 0. I'm sorry, the potassium conductance will be close to 0 because it has n to the power 4. The sodium conductance will also be close to 0 because it has m to the power of 3. So there will be no potassium, no sodium, and what will determine the dynamics of the neuron would be the leak current. So far, so good? Now let's say that we inject a short current pulse that will bring the cell from -70 to 0. A short current pulse. Let's see what will happen. The fastest term here, the fastest dynamics is the dynamics of M. The time constant of the dynamics of M is much shorter than 1 millisecond. So the first thing that will change will be the value of M. M will, within less than 1 millisecond, will converge to M infinity of V. M infinity of V is a large number. It's close to 1 if the Mermet potential is at 0. This will imply that the sodium conductance will become immediately large. And if you remember, the neuron's potential for sodium is something like -60 millivolts. So as a result of bringing the cell to 0, suddenly there will be a very large sodium current into the cell, which will immediately depolarize it to a value which will be close to the neuron's potential of the sodium current, which is around 60 millivolts. So if we bring the cell to something like 0, immediately there will be a very strong current that will further depolarize it. So one way of thinking about it, there will be a positive mechanism that if we bring the cell above some threshold, then suddenly it will depolarize as a